Okay. All right. Let's start. Let me start it. So, today my topic is using ultra-fast spectroscopy to understand relaxation dynamics in the metal nanostructures. Before I start my talk, I would like to take a minute to thank my advisors, Ken Appenberger, who is my PhD advisor. Right now, he's a professor in Penn State, and also Stephen Link and Christy Landis in Rice. I will also thank my collaborators, Peter Noander and Naomi Halas, who does not only give me a lot of advices in research, but also a lot of advices on my careers. Ron Chaojing and Chris Arkerson, who provided very high quality samples on these nanoclusters. John Setter is a theoretical physicist, help us to modeling these acoustic vibrations. And I would also thank this funding agent who provided enough money for me to do my research. Okay, a little bit brief introduction. What I will talk today. So first one, I want to talk about the system I'm interested in, which is metal nanostructures, especially gold nanoparticles. And there are two different species of nanoparticle. It is called atomic precise nanocluster and also plasmonic nanoparticles. And we want to understand relaxation dynamics, so we have to usually this dynamics is picosecond or nanosecond level. So I was using the femtosecond transient absorption to look at this relaxation dynamics, and to we want answering two very important scientific questions. The first one is, what is the smallest nanoparticle have the surface plasma resonance, and also what is acoustic vibration properties in a nanoparticles, in these gold nanoparticles. All right. Um, Size effect in the metal nanostructures. I think everybody very familiar with metals. We know that they have very good electric conductivity because electrons are free to move. Also, the color is shining, but this property is not changing when you change the size of the materials. However, in the past decades, people noticed that metal nanoparticles, uh, their property does change with their size. For example, here we give four different nanoparticles where shape is slightly different and also the size is different. We can see that at least the color or the optical responses is changing in the visible range. So how does this tunability of color is can be accessed because there is a strong light and matter interactions in the metal nanoparticles, and this gives us a very unique phenomenon called surface plasma resonance. So the surface plasma resonance is very easy to to understand. When you have photons to exciting these free electrons in the nanoparticles, this will result a collective electron oscillations on the surface of the nanoparticle. So when you increase the nanoparticle size, and this oscillation frequency will be smaller, so the plasma energy will shift into red. Because when it is so easy to engineer, and it is so easy to engineer this surface plasma resonance, we can manipulate the size. Yeah, and then there's a lot of application based on this surface plasma resonance. The first one is called bioimaging because different nanoparticles are scattering property, they're scattering different wavelengths of the light. So bioimaging, optical engineering is based on that. Also, this is collective electron oscillations. So our electromagnetic field is also important here. So the nanoparticle can have a near field coupling with your molecules surrounding the nanostructures, which give us this surface enhanced Raman spectroscopy. So very important techniques based on that. There's another application where we call it hot electron generation or hot electron decays. So when you using photons to exciting on nanoparticles, this is strong light matter interactions, right? You're creating electrons with high temperature, and this believes this can be a very critical process in these solar cell devices based on the surface plasma resonance. So all these properties or all these applications is based on one important factor. What I have been saying is they have tunability on the energy of surface plasma because when you change the size, you can change the energy of surface plasma. However, let's think about the size effect again. Is when we only have one atom of gold, in this case, the energy level is not continuum, your electrons is not free to move. So it is absolutely no plasma resonance. However, when you have few atoms of gold together, it's kind of like a molecular. Your energy level is not continuum. The dominant effect is quantum confinement. So you usually have energy levels, and your energy level is not are not continuum. But in the larger nanoparticles, which have few tens of nanometers or 100 nanometers, your nanoparticle have collective oscillations of electrons. They have surface plasma. I call it plasmonic supporting nanoparticles. So at least there are two different species of nanostructures, which is separated by size. So in 2008 or 2007, and few chemists are working, and a lot of chemists are working on this small or quantum confined nanocluster. So for example, Rong Chaojing as one of the pioneer and also my collaborator, successfully in solution phase, he made this ultra small gold nanocluster with atomic position. This atomic position or stability is coming from this super atom orbitals. Here I'm not gonna, but we found out the optical properties in this cluster is significant different as what we saw in the gold nanoparticle. There and also the application is quite different because the quantum confinement is dominant. So the kind of like a molecular system, you can pump your electrons into excited states. These excited electrons will be very useful in some photocatalysis results. So two different nanoparticles and two completely different relaxation dynamics and also completely different applications. So there's one important question nobody have answered, which is where is the onset between these two different species of nanoclusters? What's the difference on the relaxation dynamics? Because your application is different, you want to answer this fundamental process to help other chemists on their questions. So in order to understand relaxation dynamics, I think we're gonna use femtosecond transient absorption. It is being a very powerful technique. So let me briefly introduce how does it work. So for example, if we have a molecular system with three energy levels, molecular stay at the ground state, we can marry this absorption or extinction spectra. I have a single peak here, and if we use a laser pulse to exciting on the nanoparticles, which kind of partially excite your molecules from ground state into the excited states, and then we find that we're measuring the absorption again. At this moment, because you dilute the population at ground state, your absorbance will be decreasing. However, you are opening the second transitions between excited states. That's why we have a second peak in the absorption observed. And then what we can do is plotting this before your excitations, after your excitation minus before your excitations. This is differential absorbance. So we can find that this is a very typical transient absorption spectrums. The negative peak is called ground state bleach, which is monitoring how fast the electrons returns back to the ground states. And then the excited states absorption is monitoring what's the transitions between two different excited states here. What we can do next one is we can change the time delay between your pump and probe and monitoring how does these signals will returns to zero. And we can that is the lifetimes or the relaxation dynamics of excited states. Okay, so we have this pump probe measurements. We can use this pump probe measurement looking at the nanoparticle first one with plasmonics. So you using the first laser pulses to generating surface plasma as this is transient absorption spectra. The surface plasma centered at 600 nanometers. We found out that relaxation dynamics is a long range up to 200 picosecond. So we found as there's two different decay mechanisms. There's really fast decay happens in about 5 picosecond, and then there's slow decay, which can reach up to a few hundred picosecond. So And Greg Horland already published a very good paper in 2011 talking about after you exciting this surface plasma, what's the energy relaxations. The first process is plasma dephasing. Plasma lifetimes is very short, tens of femtoseconds. The second one is called electron-electron scattering because when we generate these hot electrons, electron-electron will have interaction between each other. So this is electron scattering. But these two process is very fast. Are very fast. These two processes is 10 femtosecond, 50 femtosecond. Usually my lasers is about 80 femtosecond. So it is not good enough to resolve these two dynamics. But other dynamics we do can see it. For example, the third component where we call is electron phonon coupling. This is usually 1 picosecond. As we see in the picture, it is a very fast decays in the in the kinetic traces. Kinetic trace. So two temperature model described it very well. So what is two temperature model that's saying is when you're using laser pulse to exciting the electrons, electron temperature is extremely high. However, your phonons or the lattice of nanoparticles remains at room temperature. So in this case, you are creating a temperature differences between these two different between electron gas and your nanoparticles. So the heat will flow from high temperature mode into the low temperature uh, nanoparticles. So this is called electron phonon coupling time, which will take about 1 picosecond. But if we increase our laser powers and your laser excitation energy is higher, you're generating electron gas with higher temperature. At this moment, your energy transfer process will be longer. That's why we saw this picture is your electron phonon coupling time is linearly dependent on your excitation energies. This is the hallmark, or we can use this process to identify whether this is metal nanoparticles because we need to have collective oscillations on the electrons to generating surface plasma, but and then it will have electron phonon coupling time. But like a molecular system, when you're generating this, when you're exciting on the electrons, there are only single electron transitions. It's not going to depend on your excitation wavelengths or excitation energies. After your nanoparticle becoming hot, and then the energy will heat will release to the environment. But there's another important process where we call it acoustic vibrations and coherent phonon oscillations. So in my result, today I will introduce these two different topics here, or two different process here. So thanks to my collaborator, Chris Arkerson, prepared very high quality samples ranging from 1.3 nanometers up to 30 nanometers. What we saw here is this is absorption spectras for all different nanoparticles here. For 30 nanoparticles, 30 nanometer size gold nanoparticle, we saw very strong surface plasma resonance at about 530 nanometers. But when the size is decreasing, this peak gradually disappeared. So we could like say is surface plasma resonance, the onset is happens between 1.3 nanometers and 2.5 nanometers. The next one is we use our ultra-fast spectroscopy, study all these nanoclusters. We get all the electron phonon coupling time. We found out is 144 is the smallest nanocluster, which still have this linearly dependent on your excitation energies. So it has been very clear says that 1.8 nanometer is the smallest nanoparticle which still have this surface plasma resonance and electron phonon coupling time. Look at gold 102, which is like a molecular systems because you're exciting your exciting your electrons with a single electron transitions. In this case, your lifetimes is independent on your excitation powers. Okay, so I think this has been a very topic about gold 144 because it is we are opening this field. Right now, is a lot of people who are still working on this project of these transitions from molecular into the plasmonic because they can smallly modify the crystal structures in gold 144, for example, changing their crystal structure, changing their ligand, doping some other materials. And then you want to know is there any way we can manipulate these plasmonic behaviors for gold 144? So it has been very active field, still being very active field. But I'm very happy we are kind of the first person who opened these discussions to all the society. So okay, since Golden 144 is interesting, the next one I want to introduce, what's the Foley relaxation dynamics in Golden 144? So here is transient absorption spectrums. We find out this is a ground state bleach, and the ground state bleach, hold on.